Hi, welcome everyone to my presentation about the role of linguistics in control communication with brain-computer interfaces. That's my topic for today. So I want to start off this presentation with some examples of where language and technology meet each other. And I think the most typical example is actually Google, which is like a text-based search engine that we all use every day. Of course, we also have like speech-based digital assistants on our phone, like Siri and Alexa. And another example is communication with brain-computer interfaces. And this is actually the topic I want to be talking about for my presentation. So for my paper, I'm actually investigating the relationship between brain-computer interfaces and language. And I want to do this by looking at it from two different perspectives. And the first one is actually how can we use brain-computer interfaces for linguistic communication? And the second perspective is how can we use knowledge about language to improve BCI operations? So there are actually different ways of looking at like the link between language and BCIs. So because I want to include both of these topics in my paper and this presentation, the goal is to describe how BCIs can be used for linguistic communication and also to explore how neurolinguistics and computational linguistics can be used to improve BCI operations. So I want to achieve this goal by answering the following questions during these presentations. We'll start with what is a brain-computer interface, which neuroimaging techniques are suitable for BCI control, how can we use BCIs for linguistic communications, and at the end we'll discuss how can we use neurolinguistics for BCIs. So we'll look at like the language network in the brain and also at language models. So what exactly is a brain-computer interface? So this is a system and it consists of an output, a translator, and an output component. You can also see this on the slide. And during the input phase, you're actually extracting information from the brain directly by using some kind of neuroimaging technique, and it can be any of the ones we've had in the lecture, but I'll get back to this. Then there's the translator, and this actually extracts the relevant features from the data that we've acquired, and it's followed by an algorithm that translates these features into actions for the output device. So at the output stage, the device will be able to perform a certain action based on the decision of the translator. Because this explanation of BCIs is pretty general, I want to give you an example to get some feeling of how BCIs work. So let's consider the use of a BCI in a clinical setting where a person suffers from a disability like locked-in syndrome, LIS. And people who suffer from this are completely paralyzed, but they're still consciously aware. And because a BCI uses signals directly from the brain, we can use it as a way to communicate with the outside world when a person is not able to communicate through like speech and gestures like we normally would. So in this setting, a BCI serves as an alternative way of communication. We can also categorize a BCI according to different characteristics. The first one is if it's a dependent or independent BCI, and secondly, if it's an invasive or non-invasive BCI. So let's start with the distinction between dependent and independent BCIs. A BCI is dependent if it relies on some sort of motor control by the user. And we can think of, for example, eye gaze, because this requires some muscles around the eyes to control it. And in the 90s, people actually already started to experiment with BCIs. And I want to illustrate what a dependent BCI is by explaining a classic experiment by Sutter. He instructed his participants to look at a matrix of letters, and people had to spell a word by looking at the letters of the word one by one. Meanwhile, there were EEG recordings were being made to capture the visually evoked potentials that were elicited by looking at the target letters. So these VEPs were used to determine which word was shown on an output device. The generation of this VEP is dependent on the eye gaze direction of the participant, and this means that it requires some form of motor control by the user, and that's actually what makes this example, the BCI in this example, a dependent one. So in contrast, independent BCIs do not require any type of motor control by the user. A similar experiment has been performed by using an independent BCI design, and in this study, participants had to spell a word as well, but they had to look at letters flashing on the screen one by one, so they were exactly in the same position. And therefore, the users did not have to change their gaze direction. Every letter still presented a response. In the brain, it was the P300. And this response did not depend on the eye gaze of the participant, but of the intention. And this is what makes this BCI independent BCI. So now let's look at the difference between invasive and non-invasive BCIs. BCIs require the use of a neuroimaging technique, and different neuroimaging techniques have different level of invasiveness, as you all probably know from our lectures. So an invasive technique requires the implantation of microelectrodes directly onto the surface of the brain, while non-invasive techniques do not require any type of neurosurgery or penetration of the skull. And what kind of neuroimaging techniques can we use for BCIs? Some BCI studies have used EEG, ECOG, fMRI, and PET. And as we know from the previous lectures, some signals can be derived from derived from EEG and ECOG are like visually evoked potentials, mismatch negativity, and the P300. And when we look at fMRI, we have the BOLD response, so the blood oxygen level dependent response. And PET scans require the injection of a radioactive marker to measure brain activity. So which of these techniques is the best for BCIs? Well, BCIs are very versatile in the sense that different neuroimaging techniques, signal features, brain areas, and types of output devices can be utilized to create a system that is suitable for any type of context. There's no one technique that's the best. And based on what I've read about the different applications of BCIs, EEG seems to be a very suitable technique for communication and entertainment purposes. And this is mainly due to the high temporal resolution, low cost, it's portable, and it's non-invasive. But other techniques like fMRI and ECOG, they have different qualities, but they're also often more expensive and not portable. And for example, ECOG is invasive. So these types of techniques seem to be more suited for research purposes, but also for communication with patients who have a poor quality of life. So now it's time to move on to one of the two main topics that I want to address during this presentation. And the first one is, how can we use BCIs for linguistic communication? And I want to answer this question by giving two examples. So the first example is a BCI for producing synthesized speech, and in this case specifically vowel production. And to determine the type of vowel that needs to be produced, this study by Brumberg, Bernison, and Pitt used two types of signal features of EEG recordings. The first one is contingent negative variation, and this is the change in potential that is related to the preparation for an upcoming movement. And the other signal is event-related desynchronization and synchronization, and this is a change in the sensory motor rhythm that's related to the preparation and execution of an upcoming event. So as you can see, both of these signals are related to movement, and the signals were provoked through a motor imagery task. So a stimulus was presented on a screen that required the participant to imagine a certain movement, like a bodily movement, and this then stimulated these types of signals. So another example that I want to tell you about is a BCI that has been incorporated that has incorporated a spelling device into a virtual environment. So this is pretty new, I would say. In this case, the user is wearing a headset, like virtual reality headset, while an EEG recording is being made, and the headset then provides the user with visual input, and this causes steady-state visual evoked potentials. And to complement this measure, they also use gesture input from the user. So it does require some form of motor control by the user. And this BCI speller actually resulted in 91% accuracy. And also the users all reported that they had a very enjoyable experience. So this is also good to know. So now I'll move on to the second main point that I want to make, and that's how can we use neurolinguistics and computational linguistics to improve BCIs. So again, I would like to give two examples to illustrate my point. And the first one is actually a study that I already explained in my previous presentation. This is where the researchers showed that ECOG signals that are associated with speech, like Wernicke's area and Broca's area, can be effectively used for BCI operations. And they actually showed that using covert and overt phoneme expression can be used to control a mouse. Another study used EEG signals that were evoked by imagined speech. So by having users imagine the expression of different syllables, they found changes in spectral power bands, and these changes could help to classify different types of output. So another way of using language for BCIs that seems very interesting to me is by using knowledge from the field of computational linguistics. So two types of language models from computational linguistics that have been used to improve BCIs are like predictive spelling and language model-based classifiers. And you're all definitely familiar with these language models. For example, predictive spelling. You can think about your phone coming up with suggestions while you're typing a word letter by letter, and it will provide you with the most common word based on these letters. And the downside to this is that it does not work well with very uncommon words. There are also language model-based classifiers, and these actually use probabilities of one word following another word. So instead of predicting the spelling of a word, it predicts the words and structure of a sentence. So a recent study from 2018 also combined both of these methods to improve a BCIs better, and they found a significant increase in accuracy and word rate. And I think, especially if we consider the use of a BCI for patients with locked-in syndrome, I think being able to produce words and sentences in an easier and more quick manner is really a worthy improvement for a user like that. Well, I hope that the two main points I really wanted to make came across with my presentation, and I hope it's clear now that the BCIs are useful for linguistic communication in different settings, but also that we can use knowledge about neurolinguistics and computational linguistics to improve BCI operations, even if they're not related to communication. I would like to make some final additional remarks about possible future directions of BCIs. I think in order to improve BCIs, we can use new neuroimaging techniques that are being developed, but that we can also incorporate new technologies for evoking brain signals and for different output possibilities like the VR that we've seen in this presentation. And lastly, the translation process can really be improved with AI, and this is like really a hot topic. So I think with all the development in machine learning and natural language processing, this is very useful for communication with BCIs. Well, thank you for listening. This is the literature list, and if you have any questions, please feel free to ask them now.